This is Dr. Brothers. This will be the lecture on systems for ECE3084 Section B. So last class period we talked about signals, and recall that a signal is a function that's mapping from some domain to a range. The domain we talked about, we could have things such as time, space, frequency. The list goes on and on. They can map to many different things. They can map to, for example, air pressure, voltage, light intensity, etc. And these can be, usually we will do these at the beginning as one-to-one mapping. So we'll have an equation that defines over some domain some output range. The domain is oftentimes called the independent variable, and the range is the dependent variable, because whatever these values are, the air pressure, the voltage, the light intensity, etc., is directly dependent on what the time is, or where you're at, or what the current operating frequency is. So we talked about these functions. That's the signals part. This class is called Signals and Systems. So there's another part of it. That is the systems end of it. So what if a function, which is a signal is a function that maps a domain to a range. What is a system? A system it will map one signal to another. So we can draw this. For instance, if we have an input x of t going through a system G, and the output of this would be y of t. So now we have a function on the input, a system that is remapping to another function on the output. So these are the signals, and this is the system. For our applications, we're usually working in this class continuous in time, or we could be discrete in time. So meaning, if the input is continuous, usually our output is going to be continuous. However, if we're working on a discrete system where we have an x of n, and remember a discrete system is a system that is sampled in time, where a continuous system is just like an analog output. So if we have an x of n, it goes through another system, let's call it h, that could give us y sub n. Normally we'll map continuous to continuous or discrete to discrete. However, consider the example of an analog to digital converter. The analog to digital converter is a system, and so we can have an x of t that is going to map through some system we're going to call analog to digital, and that's going to output a y of n. The equation that would represent this would look like this. Y of n is going to be equal to x of t sub s of n, where t sub s is the sampling period. So let's look at this equation for just a second. This is the equation that describes an analog to digital converter. We're going from a continuous time to a discrete time, and this is the system, and these are both signals that we're representing as functions. So we can write an overall equation that quantifies this system, where the input, which is a continuous time, is only going to be represented at values of n. N is always going to be an integer value. So this would be 0, 1, 2, 3. T of S is a conversion factor, really. Sample period, this is how many seconds we go before we sample. So this unit is samples per second. Or, I'm sorry, seconds per sample. Sampling frequency is samples per second. So this is seconds per sample. So we have seconds per sample, and N is in samples, so that does the conversion between seconds and samples. So this is an example of a system that takes in a continuous time and outputs a discrete time value. Usually we don't use this. Usually we use continuous time to continuous time or discrete to discrete. And those systems will oftentimes be treated pretty much the same way. So now, for this class, we're going to focus on a very specific type of systems. We're going to focus on well-behaved systems. There are other classes that you can take, nonlinear system analysis and advanced auto control systems, where they'll get into systems that are really not well behaved, and you have to do a lot more math in order to figure out how the systems work. For this class, we're going to keep them well behaved. So what's a well behaved system? We have three characteristics that we're going to follow for a well behaved system. The first one is that it's linear. The second characteristic is that it's time invariant. And the third characteristic is it's causal. So these are the three criteria that we're going to apply to our systems, and we're going to focus on systems that fall into this region, and we're going to throw one more criteria in. This might actually, we might break this towards the end of the semester if we get far enough ahead, but we're going to focus initially on single input, single output, which is referred to as SISO. Single input, single output, SISO. We're going to focus on SISO systems for this class. If we get far enough ahead, we might go to some MIMO, which is multiple input, multiple output, and then there's also single input, multiple output, and multiple input, single output systems. Those are the standard types. Alright, so, well-behaved system. What is linearity?